So let's get back to business. The only thing we left about time-independent perturbation theory is what to do when we have in the unperturbed problem, for example, two states with very close eigenvalues. That is the part called degenerate perturbation theory. So let me introduce the idea. Basically, it's a very simple thing to do. So let's take a look again at the perturbation result we have so far. There's a denominator. We are sitting at the end. The denominator is the difference of unperturbed energies. Say there's a state I. If it has equal the same and eigenvalue, it will be problematic. This factor will be infinite. That is inconsistent with the idea of perturbation. Terms are smaller and smaller in the perturbation series, right? But I would say, in general, you don't need to wait for this situation. Even if you see some other state I with eigenvalue very close to n, you should be careful already. So the question is what to do if you have situation like this in your H0 problem. Okay, so this refers to the H0 unperturbed situation when you have eigenvalues that are close to each other. I would like to state this problem in a very simple way. And the way out, if you understand this simple matrix question. So in a pictorial way, what we discussed so far about non-degenerate theory works for the following situation. So let's say we have a 4x4 matrix like this. Usually we have infinite by infinite, but just 4x4 here. Now, immediately you see the diagonal part. If we ignore all the ones out there, they are the unperturbed eigenvalues. So we have 2, 15, 20, 30. They are quite apart, right? They are quite apart comparing to 1. This is H prime ij. So in this situation, it is okay to apply the non-degenerate perturbation theory. For example, the correction to this eigenvalue, you can think of it as all these are pushing down on 2. By how much? First correction is -1 divided by 13. Second, -1 divided by 18. Third, -1 divided by 28. Okay, do you understand what I'm saying? Is that okay? Are you back? Okay, so now let's look at the degenerate situation. The question is here. If you have this problem, what would you do? Let's look at the problem. Let's say we have two eigenvalues, 15, 15. If we ignore all the ones, they are the same. That is rather extreme. Even if this is 14.5, you should be worried. Okay? So the question is, if you have this situation, how would you get the eigenvalues of this matrix? If you know how to do it, then you don't need to learn separately degenerate perturbation theory. What I mean is that we don't work it out exactly. We can do it exactly 4 by 4 only, okay? But we just do it approximately. What would you do? The trick is very simple. You first do this part corresponding to degenerate or nearly degenerate unperturbed eigenvalue. Listen to this punchline. Exactly. What do I mean by that? Now, this is just a 2 by 2. Of course, you can diagonalize or find the eigenvalue. It means this 2 by 2 exactly first, and then consider the remaining part of the 4 by 4 matrix approximately. Okay, now let me elaborate what I mean by that. Then you will understand degenerate perturbation theory without any effort. We want to do this part exactly. It means the following. When I write down this 4 by 4 matrix or any matrix, behind the scene, there is a basis set of functions. So I write this extra row and column to show you this. In our perturbation scheme, these are the unperturbed wave functions of H0. Understanding this, we take this 2 by 2 out, work out its eigenvalue, and then find their new eigenvectors. That goes back to the problem of epsilon, epsilon, delta, delta. The epsilon, epsilon, delta, delta problem, as you work out in your problem set, has very simple eigenvalues. It's epsilon plus delta, epsilon minus delta. So I know it because I worked that out many years ago. So it is 15 minus 1, 14. It is 15 plus 1, 16. So the eigenvalues, no problem. But you also need to find out the new eigenvectors that will make this part diagonal. Again, you can read it out if it is epsilon, epsilon, delta, delta. When you have situation with the same eigenvalue in the diagonal, it means this perturbation, this off-diagonal term here, will tend to mix these two basis set evenly. It means the following. When you diagonalize this part, the new eigenvectors are linear combination of the old basis, a -1 and a +1, and the weighting in the linear combinations are equal. You know, the same coefficient in front of this state and that state. If you don't believe me, you use this new basis on this matrix, you can find that you can form this so-called unitary transformation, and then at the end, you get this diagonal matrix. But if you work out question 5, you can just read it out. And I like just read it out rather than the very formal matrix mathematics. So we know if we change the basis by linear combining these two, then this part become exactly solved, diagonalized. And after that, we have to go back to the matrix and then recalculate all the other matrix elements after we change the basis of these two functions to the new functions. In this case, after you get all this matrix element out, the eigenvalues now are different. Therefore, you can apply our 2x2 matrix technique to get the eigenvalue. Okay, now this is the idea behind degenerate perturbation theory. Let me recap the key point. In a big matrix, if you have a part with the same diagonal values, you take that part and do it seriously. Exactly. If you do that, you already get a big part of the problem. You want this two element. 14 is already a big part of the answer. If you don't satisfied with this stage, then you transform your matrix with this new basis into another big matrix, recalculate all these elements, then you use second order again, then you will get more correction term. This is degenerate perturbation field. So let's get back to quantum mechanics. It means the following. In the unperturbed state, N and I, let's say they have the same eigenvalues. In the 2x2 matrix problem, it means they don't affect each other slightly. The H prime will affect them strongly to the extent H prime is going to couple them into even mixing of the ith state and the nth state. In matrix language, it means the following. I have a 2x2 because they are degenerate, so I take that part out. But I don't do any approximation on it. Let's solve it exactly. Okay? So this problem, write it out exactly. In the diagonal one is 0 for the first order minus the unknown eigenvalue. Similarly, and the off-diagonal elements. In the second order non-degenerate perturbation theory, we make approximation here. In the degenerate one, since these two numbers are very close, don't do any approximation. Do this problem exactly. 2x2, you know how to do the quadratic equation, right? So this is the exact result of this smaller part of the big problem. This is called degenerate perturbation theory. Okay? As I said, if you want to do even better than that, go back to the big matrix and include all the other states not equals to I. J not equals to I and not close to N. Then you can use second order perturbation to get the effect in. Okay? But in applying this in quantum mechanics very often, we just take this smaller part, degenerate part, do it exactly and stop. Don't criticize this because the physics is that if you take this part and do it exactly, the strong mixing due to H prime is already included in your answer because H prime makes the degenerate state most strongly into N. You have already taken care of it. All the others are much weaker. That's the point. Okay? So this answer, you can find it in the standard textbook like Griffin's. But here, I just use a very simple approach to get at the same answer. Once you understand how to treat problems within a small matrix within a big matrix. Okay? So now you see, the effect is the following. This is the perturbation effect, H prime. You turn, when this H prime matrix element is non-zero, then the string of it, if it is stronger, then this term will be more important. The effect is the following. Originally, without H prime, these two states are degenerate. They have the same energy. When this H prime effect is stronger and stronger through perturbation theory, degenerate perturbation theory, this degeneracy is removed, lift, so-called. Okay, so this graph schematically show you as the perturbation H prime matrix element becomes stronger and stronger, the energy difference of this originally degenerate state becomes bigger and bigger. Okay, so that is the effect of H prime. It removes the original degeneracy. Remember this point. In atomic physics, we have a lot of this thing coming up. Apply magnetic field, remove the degeneracy behind a quantum number called M. Well, in your YLM theta phi, the M. Okay, so that is again an application of this idea. We can generalize it to more troublesome cases. How about if in the H0 problem, you have 3 degenerate states? Don't worry, go to the big problem, read out that 3 by 3 and do this part exactly. You will get 3 eigenvalues, and as a function of the strength of the perturbation term H prime elements, this 3 state will split. This will go to that. All right? Now, you will see that in something called the Zeeman effect very soon in the first part of atomic physics. So the idea is very simple. When you cannot do approximation to small matrix, do it exactly. Done. That is perturbation theory. No matter it is non-degenerate, degenerate. It's the same spirit. So here are a few pages for deeper thinking and optional. Optional means won't be included in exam, all right? So we could generalize this idea to even 4 degenerate state or 5 degenerate state, like in your D state in your atom. You know, D has a L equals 2, okay? So you have a 2, 1, 0, minus 1, minus 2 for the M value. You can do the same, okay? Again, if you, this part means if you are not happy with doing the small part exactly and stop, you could include all the other states again by non-degenerate perturbation theory method. So let's summarize what we have in our hands, the toolbox. We start off empty with a few exactly solvable problems from last term. I assume you know the exact solutions to infinite well, harmonic oscillator, hydrogen atom, and the rotor. Okay? If you don't, review that. So we have this toolbox. Then we fill it in with variational method. It's a very simple method. In particular, if we work on trial wave function as linear combination of a few functions, it gives us a matrix problem, a small matrix problem that looks very similar to the exactly huge matrix problem. And that justifies truncation of the exact matrix. We further develop time-independent perturbation theory. These are the non-degenerate results. We understand the validity by looking at the ratio here. This should be small for it to be valid. And then we understand the second order correction in energy in terms of approximating a big matrix into many 2x2 matrices and add up the results. With this understanding, non-degenerate perturbation theory becomes treating two degenerate state, the 2x2 matrix exactly, and that is degenerate perturbation result. So these are the tools in our box. We are going to make use of this to understand atoms and molecules. You will be surprised how many things we can do with this set of tools. Okay, so we will do this. There are approximation methods that is beyond this course. You can learn it in advanced, more advanced QM2 or advanced quantum mechanics. But I list here for some students so that I direct you to what will happen next, although I'm not going to do that, okay? We will do time-dependent perturbation theory later in the course when we consider light interacting with atom or molecule. Light is oscillating E field, so time varying, okay? We will understand why there are absorptions, emissions, stimulated emissions, why there are selection rules. We will do it later. Wait. There are two topics, very interesting and important, but it's too advanced for our course. One of them is called WKB approximation under these three names. Basically, it has to do with, we have different regions, we have a potential with different behavior in different regions. How could we connect up the wave functions? This is applicable, for example, to nuclear decay. Inside the nucleus, some alpha particle wave function, outside some alpha particle wave function, how to connect them nicely, okay? That is one question for you to keep in mind. You want to read further, this is one topic. WKB, if you look into these names, some of them are classical physics people. Actually, they are used in very different topics, including gravitational wave, how to connect from the horizon out to out there, okay? You can also apply this kind of things. Another big problem in approximation method is about scattering. So I have a scatterer, an atom, or a particle, and then I have electron waves coming in, and they scattered out. Experimentally, you put a detector screen on this side. Sometimes you detect a scattered particle at this angle, sometimes in this angle, sometimes at that angle, sometimes not defected. So the question is how to calculate the probability that something is scattered at a certain angle theta, okay? That we can do. But I will not do it here. It's beyond our course. If you want to read into these topics, I have some references here. The first two are standard undergraduate, very good textbook on quantum mechanics. Although Griffin's everybody knows, but there are many that are just as good. So I list, the first three books are physicist books. This one takes you slightly to the edge of the beginning postgraduate level. But very clear, it started from nothing, assuming you don't know black body radiation. The last two books are for quantum chemistry textbooks, but they are just as clear and as good as the physics books. I also list some mathematics survival books here in case you need to brush up your matrix and determinant mathematics. They are not complicated, only 10 pages, you know what you need, okay? So this ends this first module of approximation methods. Let me clean up one question. There's one question from a student, how can I know after changing the basis, the small matrix will be nice? Oh, okay. Let me read it one more time. I need to think how to answer it. How can I know after changing the basis, the small matrix will be nice? Okay. Now the answer is the following. You change basis so that the small matrix is diagonalized. Meaning, intentionally, you change basis to make sure that this small one, the off diagonals are 0. Is that okay, Mr. Chan? This is the goal. Think about the problem. Give you a 2 by 2. We want at the end diagonal. What do you do? Okay. Mr. Chen, is that okay? Here's a follow-up. So is it possible that the diagonal terms are still same after that? Good question. You know what is the situation? Usually, first of all, it will not, because we know the answer. If it is epsilon, epsilon, really delta, delta, one will go up by delta, one will go down by delta. Mr. Chen, is that okay? Okay, you have worked, you will work it out in the problem set, right? Okay. And then there is another one. Let me see. You know, the chat box is so small, it grows so fast. Let me see. I'm not which one I answered. So there's a follow-up saying, so what only matter is the diagonal term? Well, you have to understand the diagonal term of this matrix. The matrix refers to the Hamiltonian. The diagonal term will be eigenvalue, and we want to get the eigenvalue. So the eigenvalue matters. All right. Let me see. So I think I answered all the things now. So we have about 15 minutes. I would like to start the part on atoms so that you can better position yourself on what is going on logically. I fill up your toolbox. And now it's time to apply your tools to some very interesting and real problems. So let me share the first introductory part in a new module that I call the physics of atoms. In this part, we are going to do the following. I assume you know the standard hydrogen atom solutions to the Schrödinger equation. I believe you have done that. What I meant is that you know what are the wave functions. You have a radial part, you have a YLM theta phi, and then what are the unperturbed eigenvalues? They are minus 13.6 divided by n squared EV. Do you know that? Okay, so these are the assumptions. I encourage you to review by yourself this H0 hydrogen atom problem. When we move on in this module, in this first part, we need those wave functions to do perturbation. Okay, so here we will add some effect into the standard hydrogen atom problem. We will discuss magnetic field effect, it's called Zeeman. We will discuss internal magnetic field effect. That is to say, you don't need to apply. It is there, internal to the hydrogen atom, called the fine structure. This is a big part in the history of physics. It is because of this fine structure observed in spectrum that pushed the development of quantum physics. Under this topic is the very hot topic now in condensed matter called the spin-orbit interaction physics. Because we have spin angular momentum, we have orbital angular momentum, that also leads us to consider how to handle them together or add them together to form something called the total angular momentum. So AM here means it's the shorthand for angular momentum. And even after we understand all this, suddenly, experimentally, there is a tiny splitting in the hydrogen spectrum as the apparatus became more and more sensitive. It has to do with proton. The nucleus of the hydrogen atom also has spin. The electron also has spin. Therefore, we have another angular momentum interaction due to this nuclear spin and the electron spin that give us something called the 1 centimeter physics of hydrogen atom. It is called the hyperfine structure, and because of this, astronomy got a big development. There is a signal that we can trace out there, because out there, if there are things, there are matter, mostly they are hydrogen. And nowadays, the biggest radio telescope in China, the 500-meter aperture thing in Guizhou, okay? The first scientific objective is to do a bigger sky survey of this so-called 21 centimeter line of hydrogen. So we will talk about all this interesting physics in this module. Then we will go beyond hydrogen. Hydrogen is only the first element, but even the first element is very rich in physics. We will do that. And after that, we will try to understand what happened or how to understand from helium on all the other elements in the periodic table. This part, our focus will be in how we can possibly handle electron-electron interaction, approximately. Once we have electron-electron interaction, the quantum mechanics problem becomes very, very difficult. That's why we have separate subject in physics called many particle problem, many body problems. They handle interaction. In our course, we will do something easier. I will try to convey to you some physical picture in how to approximate many electron problem into single electron problems. We will try to reduce helium problem into a single electron problem, a single electron living in a influence, under the influence of the second electron. So pretend that it is a single electron problem. It turns out that this idea works very well. And therefore, even uranium-92 is very complicated. Physicists, chemists are still talking about uraniums 1s, 2s, 2p, 3s, 3p, 3d, 5f, etc. This idea originally came from the hydrogen atom solution. We still keep this feature of a single electron problem all the way throughout the periodic table. We will discuss how we could do it and whether it is working. The answer of the later question is that yes, it is working. So let me set up the stage for this module. What are we going to do? The first thing is that you need to reveal some hydrogen atom quantum mechanics. Here, I just list out the necessary, the bare bone of knowledge, but you ought to fill in what you learned from the last term. I hope that you have these class notes in last term, right? So it is there, okay? So the first thing about hydrogen atom is the Schrödinger equation problem. So this one. The first term is the kinetic energy term. The second term is the Coulomb term. So this is the bare, the simplest form of hydrogen atom problem. Schrödinger, in his 1926 paper, solved this problem. And he showed that the answer is this, thereby convincing everybody that now this result was known since the 1860 or so. We have the Lyman series, Balmer series, that kind of spectral data waiting for an explanation. Bohr in 1913 cooked up his model orbits in an ad hoc way. 13 years later, 1926, Schrödinger get his wave equation and solve it for hydrogen, convincingly show people that now this is the result, believe it or not, okay? So my equation must be right in some way. That is his philosophy at that time. So this, if you solve this hydrogen atom problem, since this is spherically symmetrical, depending on R only, okay? So another part of physics you need to learn is this kind of problems, spherically symmetrical potential energy functions. When you solve this, you use separation of variables. Have you learned that? Separate the problem into R theta phi. 有冇學過？學咗，係嘛？ I hope. When you do that, the theta phi come together to give you the spherical harmonics, YLM theta phi. The nice thing of this part is that it doesn't depend on the detail of the potential form, not depending on Coulomb. It only depends on U of R only, spherically symmetrical. Okay, so that's lovely. It means this part works for all spherically symmetrical problems. Coulomb only affects this radial part. For Coulomb form, you get this Lagrange polynomials. They are special functions in mathematical physics, but you can look it up in table. The key point is that three-dimensional problem, generally you need three quantum numbers. You have an NL determining the energy in general. You have LM in the angular part. So in all, you have N, L, M as the three quantum numbers for the hydrogen atom states. You specify these three numbers, you specified an unperturbed hydrogen atom energy eigenstates. Spin is an embarrassing part of Schrödinger quantum mechanics. It is not inside Schrödinger's quantum mechanical formula sum. We have to add the spin part separately into the wave function if we want to consider up and down spin. We have the Pauli matrices, two states. But I'm not worrying about spin at this moment. But you had spin, a lot of spins in your previous course. I understand that. So these are the Schrödinger equation results for hydrogen atom. In a pictorial way, Schrödinger's results gives discrete energies for the bound states. There are many more, infinitely many more, okay? They are negative energy states. The energies are given by E1, E2, E3. E1 is minus 13.6 eV. And behind the scene, because of YLM theta phi, n equal 1, L can be 0 only. N equal 2, L can be 0 and 1. L equals 0 state are also called S states. So this is 2S. L equals 1 are P states. These are P states, 2P. Behind L equals 1, there are M equals 1, 0, minus 1. That's why I give a small bracket 3 here about the degeneracy behind L. In general, given L, there are 2L plus 1 values of M. Okay, so this is, I'm trying to level the field so that when we move on, you have this basic knowledge of the unperturbed problem. Okay, so now a question is, are these results correct when we compare with spectral data? Let me tell you that spectroscopy is an inexpensive, not so expensive, but very accurate experimental technique. So over a century or 1.5 centuries, spectroscopy has driven the development of quantum physics. In this aspect, I encourage you to look at the National Institute of Standards and Technology website in the US. This is 美國標準局啊，美國標準局 the website of it. It hosts a constantly updating database for all atoms in the periodic table. What are the energy levels, the value? What are their separation? Okay, they keep changing. When more accurate, measurements are done. Before we look at the numbers, I need to introduce the idea of wave number. Because if you talk to chemists, if you talk to spectroscopists, the scientists who do spectroscopy, they use 1 over lambda or centimeter minus 1 as the unit. Okay? We ought to know how to communicate to real scientists doing experiments. So let me introduce this. In physics, we used to use EV for energy, frequency, F for mu, Hertz, or angular frequency, 2 pi f, and so on. Okay? For EM wave light, because spectroscopy has to do with light absorption, emission. C, speed of light, is related to F nu, F lambda, or in other notation, mu lambda. So what is the wave number 1 over lambda? Very simple. The unit is centimeter inverse. It means the following. In 1 centimeter, how many wavelengths is that particular light in vacuum? Okay? So that number refers to the wavelength, how many of them in 1 centimeter. That's it. So if you have a wavelength in the visible region of this centimeter, the wave number is 10,000 wave number. That's the ballpark in the visible range. All right? So now, give me 2 more minutes. I want to show you the data, the tiny incorrect thing about what you know, okay? So if we want to look into delta in energy, difference in energy, we usually use the photon energy, h nu, in physics. But if we divide it by c, that is h over lambda. If we divide this energy difference by 2 constant hc, this is the wave number. Therefore, if someone tells you the wave number of a certain, say, level A, level B, the difference gives you the wave number, it means giving you delta E. You only need to convert this if you remember this formula. Okay? So this is the page I want to show you. 1s, I take this from that US site. I checked it yesterday. It is still this number. Okay, so it's so far so good. But if you look into the database, there are 4 other index, 4 other numbers behind this. But it's too accurate for us, so we don't need that. Okay, so what the database does is the following. The ground state is arbitrarily set as 0. Then they start telling you 1s to 2s, what is the energy difference? 1s to 2p, what is the energy difference? Okay, follow me? So this is set as 0. This to 2s, 1s to 2s, there is a certain number. But then the strange thing is it goes to 2p, it's a different number, and not only 1 number, but 2 numbers. So in Schrödinger, all this 2 has only 1 energy, minus 13.6. In data, there are 3 numbers. Similarly, 3s, 3p, okay, and 3d. Different numbers, first point. Second point, don't exaggerate the difference. You see, 28858, 28859. So they are different, but very close. So Schrödinger is 99.9% right. But if you work honestly with data, then they are different. Okay, so let me end with one picture. I just told you the following. I copy this number out. It means the following. N equals 1, one value, okay. Set it to 0 arbitrarily. N equals 2. Your knowledge last term, it is only one value, minus 13.6 divided by 4, EV. Now, data set. There are 3 different energies, okay? We want to understand this, why it is so. We need to add in some small effect due to spin of electron interacting with its own orbital motion. Spin orbit interaction will tell us at least they should split, okay? But then there are other relativistic correction that kicks in to split them a little bit further, okay? At the end, we can understand maybe 90% of this splitting, but there are 10% I cannot tell you why, because we need quantum electrodynamics to finally understand all these fine details, the information of which was given to us by the experimentalists. So let me end this lecture with the last line. Physics is an experimental science. It is not only theoretical. We relied on experimental input for us to develop the field. So I will stop here. I will state to answer whatever question you have. We will meet on Thursday again. So I will stop the recording and the lecture here.